rest of the stuff is a little bit high level stuff, but it's interesting stuff to learn about. So the ASIC design flow, whether you're doing an ASIC or an FPGA, kind of follows a similar design flow. So you have some design entry. That's basically you're entering your Verilog code. You synthesize it. Make sure that, and simulate, you're simulating here. You simulate the design, you simulate synthesized version. Then you try to partition it into blocks that you're going to put on the real chip. And sometimes it doesn't partition very good. You're going to go back here and redesign it so that it meets your requirements. This is usually what's called the front end of the design. So whether you're doing an ASIC or an FPGA, the front end is still the same, okay? And then this other part is called the back end. Let's say BE, back end design. And actually, when you go in industry, there's people that are specialized in front end design and people that are back end design. Anyway, once you've got a partition, you go into the floor planning, the placement, and the routing. That's physically how it gets put on the chip or on the FPGA. In the lab, you've been totally, in FPGAs, this is almost all done automatically. You can go in and modify this if you want, but the majority of the time, we just let the tool do this place and route. When you were generating your bit file, you'll see it go through, doing the placement, doing the routing. They're deciding where in the logic, which logic elements it goes, how I wire up the blocks together, and so on. In ASICs, not so simple. In ASICs, because we're trying to get them to go like 10 times the speed, it's really critical how these wires and where the blocks get placed. So there's automatic tools that still do the place and route, but there's a lot more manual intervention to make sure that it can go at really high speed. So these back-end designers are using automated tools, but they're putting in, usually they put in what are called constraints to say like, oh, this wire right here between this logic elements, I put a constraint. That has to be a maximum of 10 picoseconds delay or something. Or it might say, this block here that has an ALU, I want it to run at a clock of, 2 gigahertz. Anyway, they put all kinds of constraints to control this routing. For you can add constraints, but we tend not to have to worry about it. The only constraints that we normally put in is, okay, what's the high level clocking speed? And even in this in our labs, since we're using such a low clock, 5 megahertz or 10 megahertz, we don't even worry about it. The tool is like this, the speed is fast enough or slow enough so that you don't need any manual intervention. It can more normally just handle it by itself. But anyway, when we go to this floor planning, routing, maybe at the end it meets our specs. Okay, if not, it's too slow. We go back here. We might have to re-floor plan it, replacement. Or in worst case, we can't get it. We might even have to go all the way back up here and redesign the whole thing. That's a worst case scenario. But that's kind of like the ASIC design flow. Give you an idea. Oh, and by the way, at the end here, when you have this routed, you can do things like simulation. You can do timing analysis. This is on the final design. And you can do equivalency to checks to make sure, yeah, this routed stuff is equivalent to this logic gates or this design Verilog that I had at the beginning. We'll talk about this static timing analysis later on. We're going to do this manually, and then we'll say I'll show you how it's done automatically. Simulation, you've been doing this all along. Equivalency check is just sort of a tool you run to make sure everything's correct. Any questions? So that's the basic ASIC or FPGA. I could call them both FPGA / ASIC design flow. I'm not going to spend too much time on this, but thermal analysis is important. For instance, in the FPGAs that we do, because we have all this routing with capacitance stuff, they usually take a lot of power. And so when something has a lot of power inside it, like, remember we were saying, oh, maximum power we want to chip is like 100 to 200 watts. That's about the most you can. If you go above that, it starts melting. And in fact, when you get up to these numbers, we need to do special things to reduce the power density, because realize, LED light bulbs are pretty power efficient, but if you ever take an old incandescent light bulb, a 60-watt light bulb or 100-watt light bulb, and touch it, it's burning, right? It'll burn your skin. So think about putting all that power into this teeny little die inside of a chip. If you turn 100 watts just by itself, the thing would melt. So we have to remove the heat from that, and there's different techniques. So often, this is showing the example of a chip. Here's our die. It's in a package. And we've put the package with a thermal connection, some thermal paste here, and we put a heat sink on top. And so this heat sink is basically a piece of metal with a lot of fins that will radiate heat out from it. Now, the chip that we have in the lab, I don't think you've done that, but if you ever look in a laptop or a desktop, every processor will have a heat sink on top of it. And so you'll have conduction, and even to improve it further, they'll have a fan, and the fan will blow the air to remove that radiated heat even faster. So those things are done to help take away the heat to keep the temperature of this die. So this die, most die, they're only rated when they do the design of it up to about 125 degrees C. If it goes above 125 degrees Celsius, it doesn't work anymore. Even if it's not melted, it's just not functioning correctly anymore. So you can have a heat sink and some airflow. And sometimes if it's really desperate, you need to get it, they'll even put heat sinks on the bottom. So they'll have vias that go through the board that'll radiate the heat, and they'll put another heat sink on the bottom. So you can have heat sinks on the top and the bottom. Less common to have it on both sides, mostly on the top side, but those are possible. So to kind of quantify what these heat sinks do, we have a thing called the thermal resistance. So the thermal resistance is what's the resistance? Think about resistor like a normal electrical resistor to getting this heat away from that die. And we call that, we can write an equation. We can say the junction temperature, that's the temperature of this, that's the junction temperature of the die. What's it at? Is equal to, it's this theta JA, which is the thermal resistance, times the power dissipation plus the ambient temperature. So as you raise the ambient temperature, the junction temperature go up because that's the temperature out here, right? The radiant or the ambient. And so this equation kind of gives you an equation of what's happening on the die. And so if I want to keep this low, I either have to have a low external ambient temperature, I have to lower the power dissipation, or I have to lower the thermal resistance. So when we add these heat sinks, and this airflow fan, we're lowering this theta JA. We're lowering the thermal resistance to keep the die cooler. And that theta JA is kind of related to the resistance from the die to the package to the heat sink to the ambient. On the bottom, it's related to the package to the die to the package to the heat sink on the bottom. So I'm not going to go through all these equations, but this is kind of a breakdown. So this theta JA relates to the top and the bottom thetas. And these are like resistors in parallel, right? Because you can have heat go this way, you can have heat go this way. And that sort of shows that's a picture of the resistance. So they're in parallel, one's to the bottom, one's to the top, and you have the die to the package, and you have the die to the heat sink in both directions.
So when designing something in an Asic or Fpga, do we have to worry about the temperature in the sense that if it gets too hot, we have to underclock?
Well, a lot of modern chips, what they do is, like, say in your if you had a desktop or a laptop, and if you ever try to run like something that's really say you're gaming. I don't know if gaming is always the case, but if you run all the processors at maximum speed, what you can measure the temperature of your die, and what you'll see is it'll throttle back. If the thing heats up too much, it'll actually throttle either the speed or it'll turn off some of the processors.
But
So that's built into the
is that
system.
something for higher level processors, or is something that we have to deal also in ASICs?
You know what? It even happens in your cell phone. If you take a cell phone and you start watching videos or something like nonstop, you see it heat up. Eventually, it'll slow down, and the video rate will drop down, or a clock, or sometimes it'll just say, "Okay, stop video." So it happens in a lot of things today. Yeah. And if you ever see some people, if you look at really high-end desktops, this airflow is not enough. What they do is they actually put it in a liquid to remove it, right? Like they'll have a closed loop system, and they'll pipe some kind of gel through there to remove the heat even better than air. So it's a big deal. Like this 100 to 200 watt limit, people are running into it all kinds of situations. I got a liquid cooler on mine. Yeah, so liquid coolers even improve that. basically when you put a liquid cooler, you're just lowering this thermal resistance so you can handle more power dissipation. For ACE or for FPGAs, if you go above about 4 to 8 watts, then you start needing to have a heatsink plus fan. Yeah, even above 8 watts. So to get to 100 and 200 watts, you need a really good fans, you need liquid cooling and all kinds of stuff. Another thing to note is this theta JA, this thermal resistance, depends on how big the board is, and it also depends on how many layers there are in the board, because these layers allow it to dissipate the heat better. And so if you look at this, for a small board with very few layers, it's pretty high. If you got a large board with a lot of layers, then this thermal resistance drops down and it can dissipate more power. Anyway, that's a little bit about thermal analysis. We're running time. Moore's law, I don't know, nothing new about here other than on the right-hand side. Everybody looks at Moore's law and they say, oh yeah, the years go by and the number of transistor cost or the number of transistors on the chip, that's this blue curve. Transistor cost went down, yeah, great. But the other thing is the lithography. How do you make the mass is going up. It's in the tens of millions of dollars now for a modern process. So as I said, I've mentioned this a few times, super important to design your chip to work the first time. Otherwise you wasted millions and millions of dollars. This is an important slide. I'm going to introduce a concept that you may or may not have seen before. Oh, I got a liquid cooler mind. The engineer behind the lithography machines is, yeah, lithography is incredible. Like today, this lithography, probably just recently, 7 nanometer, 5 nanometer, they started using X-ray lithography. Before that, they used ultraviolet. And once they went to X-ray, everything went crazy. It's super expensive to use X-rays, and the machines that use X-ray lithography to get these 5, 7 nanometer geometry chips is really weird. Even making the mask is weird because they're non-conductive. But anyway, there's only one company, I think it's in the Netherlands, that makes all this X-ray lithography, and one machine is like $100 million or something to build it. So you got to have a lot of money to operate in this, this regime up here now with modern technology. Anyway, getting back to what was I going to talk about? Oh yeah, I know. Okay, let's say you were going to build a car. You bought a car. You have your I don't know what kind of car you have. This is your car, and your car is a I don't know, what kind of car do you like? Let's say it's a Honda Civic. Well, to get that Honda Civic, first off, there was a bunch of people that designed it, okay? And they said, oh, this is the idea. I want the car this way. I want the car this way, or whatever. And then they said, okay, let's design all these parts. First, you lose 30% of its value. When you get your car, yes, that's true. What you lose is it once you got it. But anyway, they had to design it, okay? They said, oh, I want the wheels to look like this. I want the front end to look this way. I want this trunk. I want through these windows, whatever. So the people designed that. And we had to spend a whole bunch of money designing it, okay? And when I designed it, that money that you spend on designing it, we have a term for it in engineering. We call it NRE, okay? And that stands for non-recurring engineering. So this is money that you have to spend up front to design this car no matter what, whenever you design a new car, you're spending, let's say I took $100 million to design that car. So that was the non-recurring engineering costs of designing that, okay? And then, okay, I want a bunch of these cars. Everybody wants a car. Everybody, I want to build, I'm selling I'm selling 1,000,000 of these Honda Civics, okay? Every one of those Honda Civics needs 4 wheels. It needs 4 side windows. It needs 1 engine. Da 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 da. All these are all the items that go into this, and that total costs $10,000. Eventually, we sell it for 20,000, but all the parts cost 10,000. And every time I build one, I have to buy all this stuff and put it in to build this whole thing and put it together. And I need people on the assembly line to put it all together. So that stuff is called RE, recurring engineering costs. And that means every time I build a car, I spend $10,000 on the car, and I sell it for people buy it for 20K. Okay. So when I want to figure out, well, what was the cost? How much money am I going to make for every car I sell? Well, I need to know what was my NRE plus the number of cars times the RE, and that's the total, right? That was my total cost. And then how much profit I make is what I sell them for minus what it cost, okay? So let's say I sold 10 cars. I spent $100 million plus 10 times, and let's say this is $10,000 per car. Then I spent 100 million.1, right? Because that's $100,000 for the cars to build them. And so the cost per car, I only sold 10 cars. It was about approximately $10 million per car. That wouldn't be a very good business model. It cost me 10 million to build them, and I only sold them for 20,000. I would lose a lot of money, right? But what if I sold 1,000,000 of them? So now I spent 10 million, 100 million to build them, and I sold 10 to the 6 times 10,000. So what's that? That's 10 to the 9, 10 to the 10. So that's 10 to the 10 is 10 billion. $10.1 billion, right? But I sold 1,000,000 of them, so that's basically 10 to the 10 divided by 10 to the 6. Then it cost me only $1,000 per car. Is that right? Something like, no, should be 10,000, a little over 10,000. So it cost me almost 10,000. So this 100 million became insignificant because I made $1 billion worth of cars, and it cost me 100 million to design it. I don't worry about it. Does that make sense? All that makes sense? So it turns out we have the same economics in when we're making a chip. Okay. If you make a chip, there's the NRE cost, and then there's the number of parts. So if the NRE is large, we want to make a lot of them. Okay. We want to sell a lot of them. If the NRE is small, we don't need to make as many of them. Okay. Hopefully that makes sense. So let's go back to our slide. So it turns out we have 3 kinds of ways to implement our chips. We have FPGAs, which we were doing in the lab. We have ASICs. I call it, this is a slide I got from one of the other profs, but let's call it, that's CBIC means ASIC. Same thing, custom built IC or application specific IC. We're going to assume that seems the same thing. And then the middle one is a mask gate array. And we learned that mask gate arrays, they don't require all the layers of a ASIC. So effectively, the NRE cost is lower. Okay. And so this slide shows the number of parts here. And this is the total cost. Now, the total cost up here, it's the fixed cost per part. That's our RE. Plus, sorry, the fixed cost is the NRE. So this is our NRE that we had to spend to design the chip, right? And then there's the variable cost per part times the volume. So this is our N. Oh, can't draw my N here. N. And this is our RE, our recurring engineering cost. So we have our NRE, our RE, and a number of parts. Right? So let's look at the FPGA. The FPGA, this NRE is very small. It's you in the lab designing your chip. How much you get paid? You guys don't get paid very much. So it's very low, but the parts are very expensive, okay? Like $100 or more. So if you look at it down here, if you look at the cost, if I'm only selling 10 parts for a FPGA, maybe I spend $20,000. We got the part for $1,000 and we paid you $19,000 or something like that. Well, there's 10 parts. So let's say the parts are $100. That's $1,000 and we paid you 19,000. That was $20,000. Whatever the case, it's relatively small. As we increase the number of parts, because the parts are expensive, this goes up pretty fast. This is a log scale, by the way. So it's going up. So it has this kind of a curve, okay, this blue curve. More parts, this RE is large, this NRE is small. So as you increase it, it logarithmically, it goes up in logarithmic cost, okay? So that's the FPGA. Let's look at the green curve, which is the Asic. The Asic, this NRE is really high. It's, $1 million or more to design it, right? The RE is very small. Once you built an Asic, this can be as low as $1 or $2 per part, something like that, even less some cases. So this is small. So if I have a small volume, it's very expensive because I had to spend a lot of money to design the chip. So everything's expensive. But if I have really high volume, this doesn't grow at all because the cost of the parts is so cheap, it just very gradually. And you'll see there's some break-even point right here. If you're selling more than, say, 5,000 parts here or something, don't do an FPGA. You should start building an ASIC because it'll save you money in the long run. You'll be able to build things at a lower cost. And today, like say you're doing a handset or even parts in a microprocessor in a laptop or whatever, it's all ASICs because they're selling millions and millions of parts. And so if they were doing FPGAs, their cost would be way up here. It would be hundreds of times higher cost if I try to do an FPGA instead of doing it in ASIC. So that's kind of the break-even point. The mass gate array is kind of in between. It costs more than the FPGA to design, but less than the ASIC. So it has a breaking point somewhere here, which is a lower volume. Okay. But this kind of gives you the idea, high volume parts today are generally done as ASICs, low volume are done as FPGAs. That makes sense? Oh, wow, we ran out of time. We didn't finish. How many slides? Oh, 3 slides left. Okay, we'll have to do that next day. Okay, that's it for today, I guess. Well, that was a lot of talking. Any questions before we go?
Yes. So when you design ASIC, you have to design the ASIC just for the specific product is gonna be built, or you can use the same ASIC module for different um, for different products with similar functionalities.
Generally speaking, when you do an ASIC, it's a special ASIC that your company uses in products that they build. So it's custom designed. It may be used in different products within that company, but like if Apple builds the M1